Okay, so you should have access to this now. So if we don't have enough registers, the thing that we're looking at here is the same thing that we were looking at for data flow analysis, actually, from the optimization lectures, which is whether or not we're basically looking at the liveness of variables in this program. So live at this point meaning that it is currently in use, or like when it is being used in this program. So live meaning like we need to maintain this value because it's going to be used in the future. And so this is looking at this in terms of a single basic block most of the time. Often across basic blocks, we're going to store things to memory, take them out of memory. However, we can do register allocation, over functions. We can do it over the entire program. But generally, we're going to be talking about this in context of like a basic block. So if we don't have enough registers, we have to spill registers to the stack. We talked about this a little bit before already, but a spill puts a value in memory rather than a register, requires a store instruction to save that value to memory. So basically we can take something in a register, store it into RAM, or into the cache, etc. And then whenever we need it later, we reload it from memory. We call that reload a fill. So register allocation is basically trying to reduce spills and fills in the program. Spills and fills require a store and then a corresponding load, which means going to the memory hierarchy, which means that what we just talked about with instruction scheduling, if we have to store things into memory and load them back, that means we have instructions that are going to take longer in the pipeline, which means that we might have more stalls in our pipeline. So generally, we want to keep as many things in registers as possible, and we want to keep the things that are used the most in registers as much as possible. So that decreases the number of loads and stores that our program has to do to spill and fill things from the stack. So there are multiple techniques that we can use to allocate values into registers. The most well-known technique is graph coloring. So what I'm going to teach you today is graph coloring, mostly because this is the algorithm that, if you go to a job interview someday and they ask you about register allocation, this is the thing that they're going to expect you to know. And I don't want to be I don't want to get you into trouble teaching something else and then basically having you go interview at Apple someday for the LLVM team and them ask you about graph coloring and you not know how that works. So so graph coloring is sort of the high level picture of how register allocation works. And then we'll talk briefly about the sort of LLVM technique, which is greedy allocation. So since this is an NP-complete problem, we have a solution that is an approximation, which is graph coloring. And then we have a greedy technique that approximates that and is a fairly quick and reasonably optimal solution, just like most greedy algorithms where, if we make sort of the best choice at every point, we might not reach the optimal solution. There might be a more optimal path or, a more optimal point on a graph, but the greedy solution will find an okay solution. It'll at least find the local optimal solution, even if that's not the global optimum. So graph coloring is the most common technique for this. Essentially what we do with graph coloring is we represent an interference graph between values, and we attempt to find a K coloring, where K is the number of registers that can be used for allocation. So we essentially have, if we have 4 registers, we have 4 colors, and we want to assign colors to a graph such that no 2 nodes that are connected have the same color. So we are going to do an example of this, and I have it set up. I apologize for my horrible chicken scratch writing here, but I think this is the best way to do this without a board, unfortunately. So what we're looking at here is a set of code, or a list of code that writes to some variables and uses some values as we do that. So for these types of problems, we need to know what things are live in and what things are live out, because that tells us what we have to have in a register coming in to start the process, and what we have to have in a register as we're leaving. So basically, if a variable is live out, that means we can't remove it. We're assuming we can't remove it from a register by the end of this function or by the end of this basic block. If it's live in, we're assuming it's using a register as it comes in. So like X and Y would have to be in two distinct registers coming into this program. E and F would have to be in two distinct registers leaving this block of code. And so we would need to have those in different registers. So they are basically, they interfere with each other because of the fact that they are live in or live out here. So the way we're going to solve this problem is basically we have all of these instructions that we're going to execute on the left here. We have the things that are live in and live out. And we have a graph, or at this point, we have just nodes for our graph of each variable that's in this application or in this block of code. And what we're going to do is we're just going to draw a non-directed edge, so just an edge between nodes that interfere with each other as this block of code executes. So the first question is, how do we figure out what interferes with each other in this graph? And the way that we can solve that is basically we want to draw a line under each variable. And there is a section in the notes. This is, I will replace this, but this is something that might be useful for you to sort of try this on your own, and we will have a homework problem that does this as well. Basically looking at, this structure that I have in the notes and, trying to draw the edges for yourself and using this table at the bottom to sort of map out where things are live. So I would kind of recommend like printing out this last page and, trying this on your own after lecture to make sure that you understand how this works. So what we're going to do is basically draw a line from where the variable starts being used to the last use in the block of code. So if we look at X here, X is live in. So we're going to start with X at the very beginning of the application. And then if we sort of scan through here, these instructions, we can see that the last use of X is in this line here where it says B equals A plus X. So I'm going to draw a line down to here, and I'm going to sort of leave a circle at the end of that line to say that that's the last place that we used X. Then I'm going to do the same thing for Y. So if we look at the code here, Y is live in, so it's going to start at the beginning. And it's going to go down till the last use of Y, which is at this line where we say E equals A plus Y. So I'm going to draw a line down here, and I'm going to stop at the instruction, and I'm going to leave a little circle there that says E equals A plus Y. So now, what I can basically do is look at these lines and determine if variables interfere with each other. So if they are, if we look at, basically going across, and we could draw lines across here, if two lines here are in the same sort of like temporal space, so because of the fact that like A equals X plus 2, X has to be live there because X is being used in that. Y has to be live there because Y is going to get used later in the program. That means that X and Y interfere with each other. And so we're going to draw a line from X to Y in this graph to indicate that X and Y are live at the same time in this application or in this block of code. So we essentially just need to know in this graph, when do two of these lines sort of collide with each other, right? Do we have a line for this variable at the same point in time? So if we have, a line, if A is down here, it's not. A would interfere with Y, but not interfere with X. So if we have these two lines sort of at the same instruction, that means that these things interfere with each other. If they're not at the same instruction, then they don't. And we draw a line when these variables interfere with each other in the graph below. So let's do the same thing for A. A is not live at the beginning of the program, so it's going to start to be live when we declare A, which is right here. A gets used in a few other instructions in this program, and it ends up ending its use at F equals A plus D. So I'm going to draw a line going from the first instruction that uses A down to the last instruction that uses A, and I'm going to put a little circle at the end here. So now we want to add lines in the bottom graph for A for these two variables. We can see that it is live at the same time as X is live because here we're going to use A plus X. So we need to have A and X in distinct registers at that point, which means that A and X are going to have a line between them. We're also going to need a line between A and Y because obviously these two lines conflict for quite a bit of the program. And so we need to have a line going from A to Y in our graph to indicate that they do interfere with each other. Okay, so that's all we can add for now. We need to do the same thing for B. And this is going to give us where a corner case will come up here. So B is going to be live starting at the instruction that defines it. So we need a separate register for B here. And then we have D equals B plus C is the last use of B in this function. So I'm going to draw a line from the instruction that uses B down to D equals B plus C. I'm going to draw this circle at the end here. Okay, so this is where things become a little trickier. So we can clearly see that B conflicts with A and Y because they are sort of completely covering each other, that these lines exist at the same points in time. So B is going to have a line from A to B. B is going to have a line from B to Y. The question is, do we need a line from X to B? What do we think?
Yes, I think so.
Okay, why?
Wait, never mind, I'm not sure.
I got a chat thing. Mike's saying no. Why no? Because I drew a little circle at the end.
Could you like just reassign what X is and at that point, and just call the X register B and then add A to it?
Right. So that's the sort of the trick here, is that because the reason I'm drawing these circles at the end is that this is the end of our use of X, right? So at the point that we do A plus X, we can put the result B into the value X, essentially. We can reuse that register at this point. So we don't actually have interference from X to B, because despite the fact that these are sort of in the same box, if we draw lines across here, these two are in the same box in time, but because of the fact that we are getting rid of X at this point, and we're creating B at this point, we can reuse the register. So we don't actually have interference from X to B. X and B can be the same color, and colors represent a physical register. So because of the fact that they can sort of reuse the register at that point, we don't end up drawing a line from X to B. So this is the sort of corner case where if we have a circle here indicating that we're done with the register at that point, we can reuse that register for B starting here. So that's the only sort of corner case here. The only tricky thing that we have to deal with is when we are assigning a value for the first time and we're done with another value at that point, we can avoid having the interference between those two variables or those two values because of the fact that we can reuse the register. So let's continue and do the same thing for the rest of the variables here. So C is going to be created here, and it's going to end at the same point as D. So here. So as D is created. So again, same basic principle here once we get to D. That we want to look at what values are being used here. And we see that C is going to be live at the same time. I'm just going to real quick draw the box here so we can look at this more in depth. So if we have C coming across here, it is clearly live at the same time as B, at the same time as A, and the same time as Y, but not X. So we can draw a line on our graph here from C to B. We can draw a line from C to A. And sorry that this is going to get a little dense here, and from C to Y. Okay. Same thing for D. D is going to start here. So D is going to go from B and C, and it's going to go until we assign a value into F. And then we'll draw the lines real quick across this instruction so we can see what is live at this point. And we can see that then D is going to have a link to A because D and A are live at the same time. However, we are getting rid of both B and C at this point. So we can overwrite one of those into D, and we don't actually need either of those values anymore. So we can basically say that D does not have a link to B or C. We could reuse either of those registers in order to fulfill the need for a register for D. So I'm going to erase those lines again. And basically we know that D, A, and Y are going to need links. So A is going to have a link to D, and D is going to have a link going up to Y. Next we'll do E. So E is going to come from A and Y, and it is going to be live out. So we want this to extend to the end of the program, essentially. So it's going to go sort of outside of the scope of the instructions that we're working with here. And we can see that it's going to be live at the same time as D. So E is going to have a line going to D here. E is going to have a line going to A, since A is still live there. And E is going to have a line, I guess, eventually going to F, but it's not going to have a line going to Y because, again, here we have that Y is done in this instruction, so we can overwrite Y with E. And then finally F. F is going to be the last value that we create, and it's going to be live out, so we're going to have it go to the end of the program. And that means that it is only going to be live with E here. Everything else, A and D, are going to be done at that point, so we can overwrite A or D, the register used for those, with F, and that means F is the only thing. The only thing it has to be kept with is E. Okay, so this is our interference graph now that we have. Any questions on how to handle this? Or how to create this graph? Okay, so the next thing that we want to do here is to color the graph. And we want to do this in sort of the most, like the most reasonable way. This is where the sort of NP completeness of the problem comes in. So for very large graphs, this is going to be very difficult to find these sort of optimal coloring. But again, what we can basically do is a greedy algorithm that will allow us to get a reasonable solution to this problem, and figure out that basically figure out what coloring we can use to represent this graph. So I'm going to use a couple different colors here, and essentially what we need to know here is that however many colors we have to use for this graph, that's how many registers we'll need to avoid any spills and fills. If we have too many registers for colors, or if we have too many colors for the numbers of physical registers that we have, then we'll need to spill and fill things from the stack. And when we do that, we can basically eliminate some edges because we no longer have things live at the same time. So for example, like if we decided to store the value D instead of saving it at a register, we could spill the value D to the stack here, fill it after the E equals A plus Y, and we could eliminate the interference between, we could possibly, or we could spill, or maybe E would be a better example, that we could spill E to the stack, and that way we would eliminate the interference between D and E because we could push that to the stack instead. So let's see how we do this. Basically, the general idea is that to assign colors, what we should do, sorry with the question, how do you decide which to spill? Usually we would want to spill the things that are going to be used the least. So the things that have basically a long period from definition to the next use. So Y might be a good candidate because Y is sort of coming in. It's not used in the first two instructions. It's then used here. So we could reduce Y's line to this instead. If we spilled Y, spilled and then filled, we basically eliminate those first couple instructions, and then it would not be live at the same time as X is live. That would reduce its interference. So essentially, we want to find the things that are going to interfere the most and be used the least. Is what we would want to spill and fill. But this is definitely a heuristic thing in order to sort of determine what stuff we don't want to have in registers. So essentially what we want to do here is count the number of edges going to a node and assign colors to the nodes with the most edges first. Because of the fact that these are the ones that are going to interfere with most other things in the graph. We want to find which things are going to interfere the most and assign a color to that register. So we can sort of count the edges here. X has 2, A has 1, 2, 3, 4, 5, 6. Y has 1, 2, 3, 4, 5. So I think A has the most edges in this graph. Correct me if I'm wrong, but I think everything else has 3 or less other than A and Y. So we're basically just going to assign a color blue to A. So A can be blue because it has the most things that it is touching. And so that's pretty much always going to require a register. So A, because it has such a big interference line here, it's almost always going to need its own register because it can't be shared with other things in this application. Next, we want to look at Y. So Y also has a lot of interfering edges, and it does touch A. So Y cannot have the same color as A. We need to make sure that it has a different color because it has to exist at the same time as A, so it's going to have a different physical register. So we're going to assign red to Y so that we don't have the same color there. So now we basically want to make sure that each node is not touching a node of the same color. So now we can kind of eliminate nodes basically saying that they can't be the same color as A or Y. So anything that A touches can't be blue. Anything that Y touches can't be red. And so we can then kind of assign colors based on which nodes are connected to other nodes in this graph. So we can see here that X touches A and Y, B touches A and Y, C touches A and Y, D touches A and Y, and E does not touch A and Y. E just touches A. So what we might want to do then is basically assign colors based on the fact that we do have all of these interconnected nodes that are going to interfere with these two nodes that have a lot of interference. So we can continue along the same path basically and say, okay, now that we have these two, let's find the next most connected node in this graph. And so I think the rest of them are either 2 or 3 edges. So at that point, we can choose one that has 3 edges here. We can assign a color, maybe green, to B. So B has 3 edges. It does not have, it is connected to A and Y, so it can't be red or blue. It has to have its own particular color. And then it's connected to C. It's not connected to D. So D has 3 edges. It's connected to A, Y, and E. That means we can actually assign D the same color. We can assign that green as well. Because it's not touching B, So it's okay to have the same color here. So we could basically reuse the register that we used for B for D. And that makes sense, right? Because we had this connection in the graph where we have B goes until the point that D is created. And so we could reuse the register that we assigned to B for D. Next, we'll need a new color because we can't make C blue, green, or red. So we're going to have an extra color for that, which is going to be purple. So again, I'm just sort of going from the most connected nodes to the least connected nodes here by the number of edges that are attached to that node. So we're going from, you know, the 6 nodes for the 6 edges for A down to the 3 edges for C. Okay, so now the last thing we have here is basically to clean up the rest of these nodes here. So we can look at what colors we have remaining and what nodes we have remaining. So we have 2 more nodes that are connected or highly connected. We have E that is connected to A, D, and F. X that's connected to Y and A. And F that's just connected to E. So what we can sort of surmise here is that we need E to be a different color than A, D, and F. F is not assigned a color yet. We need X to be a different color than Y and A. And so we can try to be a little, you know, intelligent here, basically say that maybe X is going to be green because we have this same principle here where X is being used and then B is going to be used. So we would probably want to assign green to X. This is fine because it's only connected to A and Y. A and Y are blue and red, so green can be attached to those. And then we need to assign something to E. E is coming from A and Y, but A and Y, I guess Y is no longer live at the point that we get to E. So it would make sense to assign E to red. But however, this isn't necessary. Like we could assign E to purple if we wanted to, because of the fact that C and Y are both going to be no longer live at the point that E is being used. We could definitely reuse the same color for E if we wanted to from C as well. So we could use purple here. And then for F, we have a couple choices. So because of the fact that F is only connected to E, we can assign F any color except for E's color. So we could make this blue, we could make it purple, we could make it green. It doesn't actually matter what we use. So this is coming from either A or D. So it probably makes sense to assign it to either blue or green. In this case, I'm just going to assign it to blue so that it takes the value, basically takes A's register at the end of this execution. Okay, so that's it for graph coloring. That's essentially the way that this works is we just draw this interference graph and then we intelligently try to color these nodes. And there are a number of heuristics. Again, the sort of the real solution to this is that we try every possible coloring and whichever coloring has the least number of colors, that is the correct solution. So for these problems, I will give you a small number of nodes or a small-ish number of nodes so that you can sort of, reason through what the best possible coloring is. Algorithmically, the only way to find this is to try every possible coloring and then see which one has the least. But we can do some sort of a greedy heuristic and basically assign based on the number of edges and look at the interconnectedness of the graph in order to determine this. So at the end of this, what we want to know is what K coloring do we have of this graph? And we can see here that we used blue, green, purple, and red, which means that this is a 4 coloring. And so that means that we need, implies that we have 4 registers that we need for this. So on most normal systems, this would mean that we don't need any spills or fills. Iteration. So essentially, these kind of group into anything that increases the static scope of the code. So anything that increases how much code we're looking at one time. We talked yesterday about instruction scheduling, and this is a big extra sort of component that ties in with register allocations. So if we move instructions around, that can significantly increase the sort of scope of a variable. So let's say in this code here, we go from what we have currently to moving E up to here. So A is computed there, Y is computed already. So we could compute E here if we wanted to. E is live out of this function. So now, instead of having what we had before where E was live just through these three instructions here, now E is live for this entire part of the such that we end up making it live for a very long time and therefore increasing the register pressure. So it's possible that we can still register allocate with 4 registers, but this would be a good practice thing to try as well, basically to move this instruction, re-register color and or re-graph color, and basically see, does this increase the scope of or increase the number of registers that we need for this. So instruction scheduling can drastically change the register allocation procedure. And same with instruction selection. So if we have instruction selection that requires specific registers to be used for specific things, that can also affect the register allocation procedures, making it easier or harder depending on how we do this. So sorry for going a little